Hi, today in Applied Calculus we're going to learn the product and quotient rules. So we learned that if you needed to take the derivative of something that was being added or subtracted, we could just go term by term, take the derivatives, then add or subtract them. Unfortunately, that is not the case if there is multiplication or division between the different functions of x we're trying to take the derivatives of. So the full proof of this is way beyond our scope, but I will kind of show you that it works and that what you would be tempted to do does not work, so that hopefully you can see that. So this is called the product rule, and it is for any time you can think of your function that you're trying to take derivatives of as the product of two other functions of x. And part of the battle here is deciding that you even need the product rule in the first place. So most students can eventually, through flashcards, memorize the product rule itself, but the weakness seems to be recognizing that you even need it. So we will talk about that. So while it would be cool if we could just take the derivative of little f, and take the derivative of little g and multiply them together, that does not work, and I'll show you in a second. But what does work is to take the first factor being multiplied first times the derivative of the second factor plus the second times the derivative of the first. And so I don't really like remembering it with symbols, because what if your symbols are different in your problem? And so this is the first of one of our calculus chants that we will have. And so this is my job. I do this for a living, and yet there's no way to write down the derivative with the product rule without at least silently in your head reciting that you are writing the first times the derivative of the second plus the second times the derivative of the first. So you really have to say that to say what you're going to do. And I like to memorize it that way versus any particular symbol, since you could see them differently in different textbooks. So as an example, if we had something like this, that is x cubed times x to the fifth. Now I understand that this is a very easy function that we could just multiply. We know that we add our exponents when we're multiplying two numbers with the same base, and then that's a power rule problem. This is on purpose. I want you to be able to check and see that what looks crazy over here does work and does give us the derivative we're expecting of 8x to the 7th based on the power rule that we already know well, and that what is tempting does not work. So this product rule says if I'm taking the derivative of the product of x cubed and x to the fifth, that I will write down the first exactly how it is times I need to take the derivative of the second plus the second times I need to take the derivative of the first. So this is going to be equivalent to the answer to our derivative, but we cannot leave the little baby ddx's derivatives that we still need to take in our final answer. So I won't always make you fully simplify, but you have to at least get past here and not have any derivatives left to take. So we have x cubed times power rule 5x to the fourth plus x to the fifth times power rule 3x squared. So notice that in first times derivative of the second, I'm just rewriting the first. I only had something to do on the ones where I need to take the derivative. And so that's why that ddx notation is so important, because I knew I didn't need to do anything here because it didn't have a ddx. But here I needed to take the derivative because I did have the symbol ddx. And once I took the derivative, that symbol is gone because I've done it. So if you're not being consistent with your symbols, you might never take a derivative when you're supposed to, or you might take it too many times because you forget that you already did. So if we simplify this, when we multiply x's, we add our exponents. So we have 5x to the 7th, and over here we have 3 also x to the 7th. Those are like terms, and we end up getting 8x to the 7th. Again, we would never do a problem this simple this way, we would have simply done the power rule, but I wanted to show you with something where we know how to check it that as crazy as this might seem, it really does give us the right answer. On the other hand, if we thought that we could just multiply them, so if we thought we could just take the derivative of x cubed and multiply it by the derivative of x to the fifth, let's see what happens. The power rule says 3x squared here and 5x to the fourth here, and when we multiply, we would have gotten 15x to the sixth. This is wrong. Nothing about it is right. The coefficient is wrong, the power is wrong. Okay, so it's by no means a proof, but I want to show you at least through one easy example that what you're tempted to do does not work, and that this product rule is what works and gives you what you're expecting there. So let's actually try one here. Again, you have to keep in mind that until we know the chain rule, which is coming up, it's going to look like all of our product rule examples are too simple and that we don't really need the product rule on them. Maybe not all of them, but a lot of them. So for instance here, how could you do this problem? Well, you could just FOIL first and then it's a power rule problem. But we need to practice on the more basic things so that we're ready when we don't have a choice and we absolutely must do the product rule, which I promise you is coming. So here, there's two big sets of parentheses. There's a clear first and second, right? Thing being multiplied together. So our derivative, when I say and write the product rule, that is me taking the derivative. So y prime is the first, exactly how it is, times I need to take the derivative of the second, plus the second, exactly how it is, times I need to take the derivative of the first. All right? So this cannot be a final answer, even if I'm not making you simplify fully. I need to just rewrite anything that does not have a ddx in front of it, but I need to go back and take the little derivatives that popped up as part of the product rule to get to my final answer. So the derivative of 3x plus 1 is 3, and then I'm copying, and then I get to the derivative of 2x cubed is 6x squared, and then the derivative of negative 5x is negative 5. So we could FOIL this out and simplify it. Just read directions. Remember that even if my math lab or your homework system shows a final answer real simplified, it does not necessarily mean that it would not have taken your answer. It just has to show it one nice way. So don't tell me that, oh, it's because I didn't simplify and the directions didn't say to simplify. Usually it means there really is an error and your answer is not equivalent to the actual answer. So for now, my focus was just on the actual product rule, and so I'm going to leave it there. We did all little derivatives that popped up as well, and this is equivalent to the derivative of this function. What you could do is FOIL this out and see if you get the same thing that you would have gotten if you FOILed from the beginning and then took the derivative term by term with the power rule. And there's at least one homework problem that has you do that. First FOIL it, use the power rule, compare that to what you get when you do the product rule, and of course you should get the same answer. Okay, so here is an example where we can't avoid the product rule even now with the knowledge that we have. 3x squared. So the way to make sure you don't miss that you need the product rule is to pretend like you are reading this over the phone to somebody. So they're not looking at what you're looking at, so you have to be very clear. So if you read this over the phone, you would say y equals 3x squared times e to the x. If you have to say times, or should say times if you're being really clear, when you're reading it, then you need the product rule. I have one function of x, 3x squared, multiplied by a different function of x, e to the x. And that's my indication that I need the product rule. So pause the video and you try it. Say that chant. first times the derivative of the second plus second times the derivative of the first, and see if you can get it. All right, I hope that you paused it and gave it a shot. You've got to do it to learn it, not just watch. So we have our first and our second, and so when we take the derivative, we have first times derivative of the second e to the x plus, just copy down e to the x, times the derivative of that first factor, 3x squared. We can't stop here. We go back and do the little derivatives that popped up, and remember the derivative of e to the x is itself, coolest derivative ever, and here we have the power rule and we get 6x. So yes, there's some things they have in common that you could factor out, but until we actually have a reason to do so, like setting this equal to 0, which will come down the road, there's really no need to put this in a factored form if it's not going to accomplish anything for us. So I hope that you got that. Again, this is an example where even right now, with the little that we know, you could not have gotten around this. It's not like the last problem where we could have foiled it out and gotten around it with the power rule. You had to use the product rule there, and you had to recognize that you needed it. So also on that page is one more for you to try, and that is 5x to the fourth times ln of x. This is another one where you can't avoid it. I have 5x to the fourth times ln of x. Those are two functions of x. I cannot just take the derivative of each and multiply them together. We didn't do a proof, but we did a little example to show you that that would not work. So take a minute and try the product rule with this, saying that chant, first times derivative of the second plus second times derivative of the first. Okay, so when you did that, hopefully you have 5x to the fourth times I need to take the derivative of the second ln of x plus ln of x times I need to take the derivative of that first 5x to the fourth. So we go back and we do our little derivatives that popped up, just recopying pieces that didn't have a ddx in front of them. And the derivative of ln of x is 1 over x. And when we get to this one here, we're just using power rule. So you can see that on this page, we have done power rule, the rule for e to the x, and the rule for ln of x. And all of that was inside of a product rule problem. So those rules that we've learned over the past few sections, you really have to get those down because they come up as the small part of a bigger problem as we go pretty quickly, right? So here, just because you could simplify, this is fine if I say you don't have to simplify, you're done taking derivatives, but here it's just so easy to cancel that x to the fourth over x would leave an x cubed, and then a lot of times you'll see numbers written in front of the ln of x just so you don't think that they're inside, even though my parentheses show I'm not. So just how you would normally see like back of the book kind of answers, you might see it like this, but both of these are equivalent to the final answer. Okay, so I said that what we would like to happen doesn't happen for products or quotients. Quotients being division. So what is that quotient rule? And so if you have a function that can be thought of as the quotient, right, or division of two other functions of x, of course we can't divide by 0. So we've got t for top and b for bottom. I know we should be formal and say numerator and denominator, but it's already a mouthful, so we'll go with top and bottom. And the order is really going to matter here because in the other formula it was an addition. Here it's subtraction. So of course with subtraction the order that you do it in affects the answer. So we're going to have to be really careful. So as crazy as it might seem, the quotient rule that does work for taking this derivative is the bottom function, exactly how it is, times the derivative of the top minus the top, regular top, times the derivative of the bottom, all over the bottom function, regular bottom function, squared. So I know that's pretty crazy. We'll do some with it and show you that it really does work. But here is the second of our calculus chants. So again, you know, memorizing this with f's or g's or t's or b's, well, it depends what your functions look like. We could even have something other than x, right, as our input variable. And so memorizing instead this calculus chant, it doesn't matter what it looks like. There is clearly a top and a bottom. It's a fraction, there's a top and a bottom. So it's bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. So while I've got some room on this page, let's remember that with the product rule, we had addition in between terms, and with the quotient rule, we had subtraction in between terms. If you think back to previous algebra content, this has kind of happened throughout. So one way to help you remember this is with the product rule, a plus sign is just a multiplication product tipped on its side, right? So those go together. And if you're doing division, which is a quotient, the minus sign actually lives inside of the division sign. So it's just one way to help you remember that addition is going to be in the formula for products or multiplication, and subtraction is going to be in the formula for quotients or division. If you go back to laws of logs or rules of exponents, which of course are related, you will see that same connection, right? When we were multiplying two numbers with the same base, we added their exponents. When you were dividing two numbers with the same base, we subtract their exponents, right? So this pairing of operations has shown up multiple places in math, and hopefully that'll help you keep it straight in these rules. So again, not a proof, but let me show you that what's tempting doesn't work and that this crazy thing does work. Again, I have chosen something that you would never use the quotient rule on because it's too simple. Instead, you would just simplify, and as I just mentioned, rules of exponents, we would subtract our exponents, and my original function is just x squared, and so we know its derivative from the power rule is 2x. So that's really what you would do if you saw this, but I want something where we know the answer and we can check it. So what is that crazy quotient rule? That quotient rule says the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Here's another place we need a review of rule of exponents, right? A power raised to a power, we multiply our exponents. So we have x cubed, just like with the product rule, we now need to go back and do the little baby derivatives that popped up as part of the quotient rule. So I'm here, and I'm using the power rule, 5x to the 4th, minus just copying here, but then I get to a ddx where I need to do something. And once I've done it, that symbol is gone. So that's a 3x squared. And we just talked about multiplying our exponents, so do be careful there. It's going to matter. That is x to the 6th. So a little bit more cleaning up to show that we really are getting the same thing we talked about over there. Up here we have 5x to the 7th minus 3x to the 7th over x to the 6th. These are like terms. 2x to the 7th over x to the 6th simplifies to just 2x. And that is indeed what we had gotten over there. So again, you would never do all this work when it's that simple, but I wanted to show you that it really does work with something that you're more comfortable with. Again, as we talked about with the product rule, if we did what's tempting, so if we thought that we could just do the derivative of the top divided by the derivative of the bottom, we would get 5x to the 4th over 3x squared. So if we tried to simplify that, we'd have 5/3 x squared. Again, nothing about that is right. We know the answer through tools that we've known for a while, and that answer is 2x. Neither the coefficient nor the power is right on that. So make sure you mark that out. That is not correct, and the quotient rule is going to be what's correct. All right, so let's actually try this on a real problem. So this I cannot avoid the quotient rule on. There's no way I can just simplify that and make it so that I can get around it. So we have a clear top and bottom, and we are going to do, let me get my blue. The derivative is the bottom times the derivative of the top minus goes with quotients and division, the top times the derivative of the bottom all over the bottom squared. All right, so we can go back and actually finish those little derivatives. So we have x minus 2. Now we take the derivative 2x minus 5, copy down the minus, copy down that function, and now the derivative of x minus 2 is 1. So of course you don't have to write the 1, but I want to show you that I did each piece. And then it's all over the bottom squared. So on one this simple, we really probably should FOIL out and simplify the numerator, right? If we FOIL this and distribute our negative, we will get some like terms, and we can simplify that. I am out of room. Also, when we get to more complicated functions, I won't make you simplify it. But the thing I want to show you from this form is it is going to be very tempting to cancel this. But it's highly illegal, and I know you never would. So I cannot cancel this because that other term, here's one big term separated by a minus from another big term, does not have an x minus 2 in it. This is going to be tempting every single time. Why? Because of the formula. The formula is bottom times da-da-da-da over bottom squared. So every single time you're going to see them there, but they cannot be canceled, at least at that point, because there isn't one over there. Over there we had taken the derivative of that term, so it's going to be different. So just be careful. Either you're just simplifying the numerator here, or depending how complicated it gets, I may say you don't have to simplify at all, but do not make that a legal cancellation. Okay, so here is another one. We have to use the quotient rule. There is a top and a bottom. I cannot take the derivative of the top, derivative of the bottom, and call it a day. It just does not work. Instead, I need to apply that quotient rule. So you need to say that chant as you do it and write it down. Really, just that writing it down is the most important thing. Then you know how to take those little baby derivatives that popped up in there. All right, give it a shot. Okay, I hope you gave that a try. And our first step, we should have bottom times derivative of the top minus top times derivative of the bottom all over bottom squared. And you're just writing that and saying, okay, d dx, and then just copying and pasting the tops and bottoms into the right places in that chant, in that formula. Then you go back and take the derivatives. Here are the power rules. And then for our other d dx, it's e to the x plus 2. The derivative of e to the x is e to the x, and of course the derivative of 2 is 0. So that's why that looks that way. And then over the bottom squared. And so we could do some foiling, but nothing is going to actually cancel with the denominator, so it's not really going to get us anywhere, and we can leave it just like that. All right, so yet again, showing you that we are going to keep seeing these equations of tangent lines. Just what kind of functions we're doing it with is going to keep evolving as we learn more. And so remember that we always need a point, and we're missing a y in particular, and a slope. So for the point, we use the original function. We do f of 2, the original. And for the slope, we are going to end up doing f prime of 2, the derivative. But we'll have to do a little work to get there. So for the point, f of 2, we get 2 minus 8 over 3 times 2 minus 4. That's negative 6 over 2, or negative 3. All right. That is going to be our y value, so we now have the point 2, negative 3. For the slope, we need to plug 2 into the derivative, but we first need the derivative function. The function is a quotient. There's no way around that. And so I need to apply the quotient rule when taking its derivative. So for that derivative, it will be bottom times the derivative of the top would be just 1 minus the top times the derivative of the bottom would be 3 all over the bottom squared. So I wanted to show you that as you get better at these product and quotient rules, you may not show every single step with the little d dx's, but you still have to do that. You have to take those derivatives. So if you get comfortable and you get to a point where you can do this, that's fine. And just say the answers, as you're doing the chant. So we will clean this up a little bit since we need to plug in and do things with it. So we have 3x minus 4 minus 3x plus 24. Okay, and so we do get some cancellation of our 3x's, and that leaves us with a 20 in the top, it looks like. So our derivative is 20 over 3x minus 4 squared. And so now remember that this is not a slope. So don't start writing an equation of a line with this in it, because that would not be a line. A line has x to the 1 power. This is some crazy fraction with an x that's eventually squared. So remember, the derivative itself with x's in it is not the slope. The derivative evaluated at a point gives us the slope of the tangent line at that point. A slope is a number, right? If we have y equals 3x plus 7, the slope is the 3 part, not the part with the x in it. So our slope is f prime of 2, which is 20 over 3 times 2 minus 4 all squared. So that's 6 minus 4 is 2 squared. So we end up with 20 over 4, which is just 5. So we have a slope of 5 and a point here of 2, negative 3. And so we write the equation using your favorite method. Once we get here, they're all the same. It's like algebra class. You have a point and a slope. It doesn't matter. None of this mattered. The only thing that has changed in writing an equation of a line is that we are specifically talking about the tangent line, and the slope of the tangent line at a point is the derivative at that point. Our derivative was of a function that was a quotient, so we needed the quotient rule. So we've got y minus our y equals our slope times x minus our x. So we have y plus 3 equals 5x minus 10. And then bring that over, and we have 5x minus 13. So as always, if you were to graph this function and this line, you should see that they share the point 2, negative 3, and that the line rides alongside that function and does not cross through it, but rather describes how steep it is at that point. All right, so for our last problem for you to try, it is a word problem, but it really just boils down to a function that happens to be a quotient. So this is the total sales, and we need to be careful here. Our units are thousands of games, because a lot of times when we talk about sales, we think about money, but here it's how many of the games we've sold. So of video games, T months after the game is introduced. So this is going to relate to those way back when we first learned derivatives, kind of writing sentences and interpreting what it means in the real situation. So we have this function 150t over t plus 3. So when we're at this point and we're just plugging in 12, we could do that right away. But for the derivative, remember, it is a quotient. It is a fraction that has your variable in both the top and the bottom, and you cannot just do the derivative of each one and divide. You have to apply that quotient rule to do that. So take a minute and see if you can at least take the derivative and then maybe plug the numbers in, and then we'll check it and also talk about interpreting the results. Okay, so let's look at part A. For our derivative, we have quotient rule. Bottom times derivative of the top is 150 minus 150t, so top times derivative of the bottom is just 1. If you took an extra step to show the ddt's here, because it's t, that is perfectly fine. And then it's all over the bottom squared. So if I distribute, I get 150t plus 450 minus 150t. The 150t's cancel, and I end up with 450 over t plus 3 squared. So part A was just find the derivative. It'll still have t's in it, and that is our derivative function. So then in part B, we're supposed to find s of 12 and s prime of 12. So here is s of 12, and I'm going back to the original function. Be careful because we've got two functions floating around, and plugging 12 in, we get 120. But when we go to interpret it, we have to remember that our units were in thousands of games, so be careful. The way we would interpret this is 12 months after the game was introduced, because we were in months after the game was introduced. This is just the original function that tells us total sales. Total sales are not 120, not $120, 120,000 of games, right? 120,000 games. So 12 months after they released the game, they had sold 120,000 games. Now for plugging into the derivative and interpreting it, for our derivative function, so just make sure you're using the right function, plug 12 in and evaluate, you get 2. Okay, well, what does that actually mean? Remember, the second you see derivative, it's some sort of rate of change, and that has to play into your sentence that you write. So 12 months after the game is introduced, total sales are, if it's positive, increasing, if it's negative, decreasing, but it's positive. So total sales are increasing at a rate of 2,000 games per month. So remember that your units for any derivative function will always have a per in them. It is always units of the output per units of the input. So our output was total thousands of games, and our input was the number of months since it was introduced. So that's why it's 2,000 games per month that we were increasing at that rate. So get that down. We now have had multiple places where you have been told that after doing something, you will have to actually interpret it as a sentence. And so you've seen problems where you didn't even have to do any math. I just told you the answer, and then you had to write the sentence. So get comfortable doing that. Do some practice with that. And then lastly, it says use what you found to predict the total sales after 13 months. Well, this goes back to what we talked about, a little bit different background story, but what we talked about back in marginal analysis, that we found that the total sales were 12,000, and we're talking about the slope of this graph that we've got this tangency. And so at this moment, the slope, which is modeled by the slope of the tangent line, looks like this, is whatever it is. It's 2 for us, 2,000. And that means that if you move over one input, which is months, that you should move up by this much. And we found that it was 2,000. So remember, the closer we are, the closer this approximation is to what really happens. But that's the idea, is that we're using what we know about the rate of change right now to predict what we will get 1 unit from now. And so we had gotten that it's 120,000 right now, and that at least at this moment, because it keeps changing, but at this moment, things were increasing at a rate of 2,000 games per month. So that means that in the 13th month, you would be at 122,000 games after those 13 months from the introduction of the game. So with our product and quotient rule, it's really going to take practice, practice, practice. You've got to get those chants down. You cannot arrive to your first test not knowing that forwards and backwards. And also, again, practice with recognizing that you need it. So even if you didn't do some problems, if you found a set of problems, practice with just saying, what rule do I need in order to do that? And we'll do a little bit more with that after the chain rule as well. So get down your power rule, your rules for exponentials and logarithms. We had a few of those, and then now we have the product and quotient rule as well. Coming up next is the chain rule we keep talking about, and that will help us to take the derivative of even more complicated functions. Isn't that exciting? All right, see you next time for Applied Calc.